All right, welcome back everyone. This is Calculus 1, Lecture 2, Introduction to Limits. So first of all, what is a limit? If a function f of x becomes arbitrarily close to a single number L as x approaches c from either side, then we say that the limit of f of x as x approaches c is known as L. Okay, and we've got some calculus notation for what a limit looks like here. LIM, that stands for limit, of course, as x, and we denote approaches with this arrow over here, as x approaches c of f of x. This is the function in question, or the quantity in question that we're taking the limit of, or valuing the limit of. And this on the right side is that limit itself, L, whatever that function is approaching as x is approaching c. So let's break this down kind of graphically and look at what this actually means. So you've got this function f of x here in yellow. On the x-axis, I've got an arbitrary point c. It could mean anything. You could say c could equal 2 or something like that. It doesn't really matter. On the y-axis, I've got L. All right. So c comma L is this point in the middle over here. So what's going on is as x is approaching c, and along this function, I'm tracing along this function, as I go to the right, with the x values, they get higher and higher, they get closer and closer to c. What we're noticing is the y values are getting closer and closer to L. Okay, and the same thing's happening if I start on the right side, and I move left. I move my x values left, closer and closer to c from the right side. The y values are dropping, and they're getting closer and closer to L as that happens. And that's all this is saying. It's saying the behavior of x as it goes to c matches with this behavior of f of x going to L, or the y value going to L. So these are paired behaviors. They're both kind of going simultaneously. Both things are happening at the same time. Okay, and we're going to see later on this limit, in order for this limit to exist, this has to be happening from both sides. So you might say that from the left side, the limit as x approaches c, from the left, this little minus sign is going to mean the left. This of f of x has to equal the limit as x approaches c from the right of f of x. That's what this plus sign over here is. So these two limits have to be going to the same place in order for this whole or complete overall limit to exist. Okay? So that's all a limit is. Now, last time we saw, right, we were talking about average velocity and instantaneous velocity, and we saw that h being the duration of time that we're considering for our velocity, as h got closer and closer to 0, as it got more and more minimized, and that duration shrunk, it got smaller, we saw that the average velocity of the object approached 640 meters per second. So in other words, we could have said that, using our new limit notation, the limit as h approached 0 of s of h, so s was our position function dependent on h, right? That's the variable that was in question, equals 640 meters per second. Okay, so and remember, as duration got smaller and smaller, that average velocity got closer and closer to the instantaneous velocity, which was this 640 meters per second. All right, so now let's look at an example. So say we've got this function f of x is equal to x cubed minus 1. Okay, we want to plot this function, but we're going to see that we have a little bit of a problem here, right? When x is equal to 1, that's going to cause a 0 in the denominator. So we're not really sure what to expect, because that's an undefined point on our function. Okay, well, we can go ahead and kind of investigate the behavior of this function if we write out a table. So we can experiment with a bunch of x values and y values, which we've got labeled here as f of x. And let's try to create a range around that 1 and see what happens as we get closer and closer to 1. So I've got 0.75 on the left And I'm going to build up to that 1, 0.9, 0.99, 0.999. And the same thing on the right side. I'm going to have 1.25, and I'm going to try to get closer and closer with those x values to x equals 1. Okay, so I'm approaching 1 from the left and also approaching it from the right. I want to see the behavior. Now, it seems that as x approaches 1 from the left, f of x seems to be getting closer and closer to 3. And we observe the same thing from the right side. I start out with 3.813, and as my x values are getting closer to 1, my y values are dropping. They're getting closer and closer to 3 as well. So it looks like that no matter what side we approach 1 from with x, f of x is going to approach 3. Okay. And now let's take a look at how that's going to look graphically. Okay, so we've got our x-axis here, our y-axis here. I've got my function f of x in yellow. And I'm going to have a hole in the graph at x equals 1. It's undefined. Right? We cannot divide by 0. However, as my x values are coming in from the left, they're getting closer and closer to 1. F of x, or y, is approaching 3. And the same thing's true. As I come in from the right, my x values are getting closer and closer to 1. My f of x values are getting closer and closer to 3. So although we can't actually define the value at x equals 1, we cannot say that we have this point 1 comma 3. Using our new notation, what we can say is that the limit as x approaches 1, and this is true from either side, of our function f of x is equal to 3. Okay, so this portion is talking about your x-axis, or your x behavior, and then this part is sort of talking about your y behavior. What's the function behavior in the y direction? Okay? Just like we're saying, although x cannot actually equal 1, we can get infinitesimally close and still see that f of x is moving infinitesimally close to 3. And that's infinitesimally is talking about this pattern that we're trying here, where we're just getting as close as possible to 1. We can always do this pattern forever and ever, right? We can just keep adding another 9 in from the left side. We can keep introducing another 0 from the right side, and we're going to get as close as we can possibly get to these values. Okay. Now that's a tabular method, and it works and it helps, but it's a little bit tedious. So fortunately, we don't always have to rely on the tabular way of trying to investigate what a limit is. We can also do the same process algebraically. So let's see how that looks. So again, I've got my limit notation, the limit as x approaches 1 of my function x cubed minus 1 over x minus 1. Now, I can use a property here if I recognize that, well, 1 is really just the same thing as 1 cubed. Right? 1 is a perfect cube by itself, right? So I can actually go ahead and I can use what's called the difference of cubes formula, which expands like this. If I had a cubed minus b cubed, this can become a minus b times, in parentheses, a squared plus ab plus b squared. And if I had the sum of cubes I was dealing with, if this were a plus sign instead, I could expand it like so. A plus b times a squared minus ab plus b squared. Right, so the first sign is the same as whatever we started with, and that middle sign in the second part is going to be the opposite of whatever we started with. So these are the same. That's going to be the opposite. Okay, so these are really just convenient formulas, especially when we have to do some sort of algebraic expansion in calculus. Okay, well, now the nice part is I see that I've got an x minus 1 on the top and an x minus 1 on the bottom. And I can actually go ahead and I can cancel out that problematic factor. Right, that x minus 1 on the bottom was what was preventing me from evaluating this function at x equals 1 in the first place. And now that it's gone, I'm going to be left with just a simple polynomial. The limit as x approaches 1 of x squared plus x plus 1. Okay, now, in this last step, because I'm not going to get an undefined value, I'm actually free to go ahead and directly substitute c equals 1, so c was whatever our x was approaching. I can just throw that in for x right in here. And let's see what we get. We're going to get 1 squared plus 1 plus 1, and that's going to come out to 3, which is exactly what we found from our table. As x approached 1 from either side, f of x approached 3. So we're seeing the exact same result algebraically in what I think is a much more convenient method. Okay, so just be sure when you're doing this, when you are determining limits algebraically, until you're doing that direct substitution step, be sure to keep rewriting your limit, because this is what we're evaluating. Until we have actually evaluated the limit, that little portion has to be there. Okay. So here we've got a couple of examples for you to try. You can try determining the limit algebraically for these functions. You can go ahead and pause the video and give these a try for a moment. And now, let's go through them. Okay, so first of all, for example A, we've got the limit as x approaches 1 of x squared minus 1 over x minus 1. So this is really similar to the one we just looked at, but instead of a difference of cubes up top, now we've got a difference of squares. And we can go ahead and we can make use of that same formula. So this is of the form a squared minus b squared, which is going to expand to a plus b times a minus b. So I'm going to change this x squared minus 1 into an x plus 1 times x minus 1. And I see that same convenient result. My x minus 1 factors are going to cancel. So I'll be left with the limit as x approaches 1 of just x plus 1. Now we're free to go ahead and do that direct substitution. We can drop this limit notation now. 1 plus 1 is just equal to 2. Okay, so that's a really straightforward example. Then we've got example B. The limit as x approaches 0 of, in the numerator, 2 plus x, the quantity cubed, minus 8, all of it divided by x. We see the problem right now. If we were to go ahead and we're try to plug in 0 for x, we're going to have a 0 in the denominator. So our goal is to try to see, right, and we're seeing the same pattern here. We're going to try to expand this numerator and see if we can cancel that x out. We want to try to cancel out whatever that problematic factor in the denominator is. And then we can actually go ahead and we can evaluate this. All right. So you're not going to be able to always do that in every single case, but you can in a lot of cases. Okay, so let's see how that might work here. So I'm going to rewrite this 2 plus x cubed as the same thing as 2 plus x times 2 plus x squared. Okay, and now 2 plus x squared, I'm just using my a plus b squared formula. This is a squared plus 2ab plus b squared to expand that second part. So I'm going to have 2 plus x times 4 plus 4x plus x squared, all of it minus 8, all of it divided by x. We go ahead, we distribute, so multiply all these terms out, and I'll be left with 8 plus 8x plus 2x squared plus 4x plus 4x squared plus x cubed minus 8. And now right away I can see that my constants will cancel out, which is a great sign, right? We would love to be left with only x terms in the numerator so that we can factor out an x and cancel it out with that denominator x. Okay, and that's what we're going to see is exactly what's going to happen. So right here, all I'm doing is I'm combining like terms where I can. So I'm left with x cubed plus 6x squared plus 12x, all of it divided by x. Go ahead and factor out that x from the numerator. We'll be left with x times x squared plus 6x plus 12. These cancel. And now I just have that polynomial from the top. And now I'm ready to go ahead and do my direct substitution step. Go ahead and plug in 0 for x. You can drop that limit notation now that you're doing direct substitution. And you're going to get that this limit is equal to 12. All right, example C. Now I've got the limit as x approaches 0 of the square root of x plus 1 minus 1, all of it divided by x. So same pattern here. We've got an x in the denominator. We've got the limit as x approaches 0. We cannot plug it in as it is. So we want to see if we can algebraically rearrange this somehow to deal with that x. Cancel it out. We can. Now, when you have a radical like this, plus or minus some sort of term, some other radical, constant, whatever it is, these are difficult to deal with as they are. Right? We can't just break this apart or something like that easily. So the strategy that we're going to try to make use of is treating this a minus b as just a factor, right? Just treat that whole radical as some sort of a, and whatever comes after it as a b, right? So in this case, you have a subtraction sign. You may have an a plus b format, right? Now, if I have an a minus b, if I were to multiply that by a plus b, that's going to give me my difference of squares. Okay, so that's the strategy we're going to try to employ here. We want to try to get rid of this square root, and the best way to do that is to get these terms squared. Okay, so we can't just square them out, right? We have to multiply by something strategic in order to do that, right? And that's called, in this case, the conjugate. So we're multiplying by the conjugate. So if we have a minus b to begin with, we're going to be multiplying by a plus b over a plus b. We're going to multiply the top and the bottom. We can't just do one side of that. Okay. And if I had if I had a plus here to begin with, I would have multiplied by a minus b over a minus b. Okay, but the effect is the same. So this is to get this into an a squared minus b squared format. Both of our terms are squared here. This radical is going to cancel out. And there's no need to distribute this. We can just leave that as it is for now. Okay, so we're going to see that the top is going to become x plus 1 minus 1. And the bottom is x times the conjugate that we had multiplied by. The square root of x plus 1 plus 1. Okay, this is really good because our constants are going to cancel out in the numerator. We're left with just an x term. That x is going to cancel out with that x that we originally had in the denominator. So now we're just left with 1 over the square root of x plus 1 plus 1. And note, this is mathematically equivalent to exactly what we started with. This is just a different form of what we started with. But this way, we can actually go ahead, we can actually substitute in x is equal to 0 and get some sort of definitive answer, okay? So plug in that 0, we can drop the limit notation now for direct substitution. We're going to get this limit is equal to 1/2. All right. And finally, example D. We've got the limit as x approaches -1 of 4 minus x squared over x plus 2. Okay? So right away, you might notice this also is just a difference of squares. That can be factored into a plus b times a minus b. Okay? So that 4 minus x squared becomes a 2 plus x times 2 minus x. Now, no, you don't immediately see this as the same thing, right? 2 plus x and x plus 2 are really the same thing, though, right? Even if they're not given in the same order. Now, I just want to make a side comment that if we had gotten, we have this 2 plus x, 2 minus x in the numerator. If we had an x minus 2 in the denominator, just be careful with that. So this, x plus 2 and 2 plus x, we can just swap, no problem. But in order to make x minus 2 and 2 minus x kind of look the same, we need to factor out a negative. Okay, just a -1. So just keep that in mind. That would add a negative sign if that were the case. But in our problem, in this example, we can just go ahead and we can just cancel these right out. Our denominator is gone. And we're left with the limit as x approaches -1 of 2 minus x. And you can throw that into there. And you're going to get 3. Now, something that's interesting here is, could we have just put in -1 from the get-go? And in fact, we could have. This -1 would not have made the denominator undefined. Okay? So you don't actually always have to simplify ahead of time. You can just kind of take a look, and your first step should be to take a look and see if I can just do direct substitution right away. Okay? So those are examples. Now let's talk about instantaneous velocity as a limit. So recall that the average velocity of an object on a time interval from A to B was given by this formula. The average velocity is S of B minus S of A over B minus A, S being that position function. The instantaneous velocity at t equals A is what we said was the limit as B approaches A. Okay, and we can write it in this notation. The instantaneous velocity is limit as B approaches A of the average velocity formula, and then you can go ahead and you can plug that in. Or if we use that notation where B is equal to A plus H, it would look like this. The instantaneous velocity is the limit as H approaches 0 of the average velocity, and we're going to get this S of A plus H minus S of A, all of it divided by H. Okay. Now let's see how that actually looks. Let's try it with the limit in an example problem. So consider a moving object whose position function is given by S of t is equal to t squared. S is measured in meters, t is measured in seconds. Part 1, let's determine the most simplified expression for the average velocity on the time interval 3 to 3 plus h, where h is greater than 0. Okay, so this is a really helpful step that we don't have to always do our simplification when evaluating a limit. If we can, let's try to simplify that formula ahead of time. Okay, so we're plugging into our format. Right, this is our S of A plus H minus S of A plus H minus A. Okay, and our function is really simple. It's just squaring whatever we had. So this just comes out to 3 plus h squared minus 3 squared. We expand the first part. Then we got that minus 9. Our 9's cancel. We're left with 6h plus h squared over h. And that simplifies nicely to 6 plus h. Okay, now part 2 says determine the average velocity on the interval 3 to 3.2. So 3.2 is obviously our 3 plus h, which means our h value is just 0.2. And then we can go ahead and we can plug that into here, into our simplified average velocity formula. 6 plus 0.2 is going to be 6.2 meters per second. Okay. Part 3 says determine the instantaneous velocity at t equals 3. Okay, so now we're going to make use of our limit. So the instantaneous velocity is going to be the limit as h approaches 0 of our average velocity. And since our average velocity is so simple, we don't have any sort of problematic denominator, we can just go ahead and use direct substitution pretty much right off the bat. So you just plug in 0 for h, and you're going to get 6 meters per second. Okay, so the average velocity was a good estimate for this, but we're going to be able to calculate the exact instantaneous velocity at that second, t equals 3, using our new limit method.